Corrosion grouping. Based on how it is identified. Understanding corrosion involves looking at how it affects metal. By observing the way it looks, we can identify the type of corrosion it is, often just by looking with our eyes, but sometimes we need to use a magnifying glass. The different forms of corrosion can be categorized into three groups by the way in which it is identified. Group 1. Corrosion identifiable by visual examination. They are uniform, pitting, crevice, fill form, pack rust, galvanic, lamellar. Group 2. Corrosion identifiable by supplementary means of examination. They are erosion, cavitation, fretting, intergranular, exfoliation, and dealloying, also known as selective leaching. Group 3. Corrosion verification by microscopy. They are environmental cracking, stress corrosion cracking, SCC, corrosion fatigue, and hydrogen embrittlement. Let's starting from Group 1. Corrosion identifiable by visual examination. Number 1 is uniform. Uniform corrosion is a type of corrosion where the damage occurs evenly over a metal's surface. This is the most common type of corrosion, but it's also the easiest to predict and prevent. There are two main types of uniform corrosion. The first is the kind that makes a surface look unappealing, which can be easily controlled using methods like cathodic protection or coatings. And the second is the kind that adds color and character to a surface, which can be seen in patina on copper roofs or rust on weathering steels. However, uniform corrosion can sometimes be a sign of a more serious issue. For example, if a protective coating breaks down, it can lead to surface corrosion. This can make a surface rough and may eventually cause more severe types of corrosion. Surface corrosion can be seen when a metal's surface becomes dull, etched, or oxidized. It may look like staining or discoloration. If left unchecked, surface corrosion can worsen over time. To summarize, uniform corrosion can be controlled and is often not a major concern, but surface corrosion is a warning sign that a more serious issue may be developing. Pitting corrosion. Pitting corrosion is a type of localized corrosion where small holes or pits are formed in a material. It's more difficult to detect and predict than uniform corrosion, which is why it can be more hazardous. There is definition some words used in term of pitting corrosion. Pitting, a type of corrosion that forms cavities on a metal surface in localized areas. Pitting factor is the ratio of the depth of the deepest pit to the average penetration as calculated from weight loss. Pitting resistance equivalent number, PREN, is an empirical relationship to predict the pitting resistance of austenitic and duplex stainless steels, which is expressed as PREN equals CR 3.3, MO 0.5 W, 16N. Causes of pitting corrosion. The first is localized chemical or mechanical damage to a protective oxide film. The second is poor application or damage to a protective coating. The third is non-uniformities in a metal structure. And the fourth is presence of an abnormal cathodic site surrounded by normal surface. Effects of pitting corrosion. The first is localized loss of thickness in a material. The second is acting as stress risers, which can cause fatigue, stress corrosion cracking, and catastrophic failure of a system. Examples of risk consequence. Number 1 is a single pit in a gasoline line can cause a catastrophic failure, like the Guadalajara gasoline pipeline explosion that killed 215 people. Number 2 is a local cathode, abnormal, can remain impervious to corrosion, as shown in an aluminum specimen image. Number 3 is crevice corrosion. Crevice corrosion is a type of localized corrosion that happens when a small area, like a gap or a crevice, is trapped by a material, like a gasket or washer, and the liquid, like water or a solution, inside the crevice doesn't move. This can be found in areas with trapped liquid, such as, under seals, like gaskets or washers, insulation, fastener heads, surface deposits, disbonded coatings, threads, lap joints, clamps, etc. Crevice corrosion is caused by changes in the liquid inside the crevice, including: the first is less protection, depletion of inhibitors. The second is less oxygen. The third is more acidic conditions. And the fourth is more aggressive ions, like chloride, which speed up corrosion. When there is limited oxygen flowing into a small space or crevice, a difference in oxygen levels forms between the small space and the surrounding larger area. This can start a chemical reaction that can eventually damage the surrounding area. Initially, the oxygen level inside the crevice is the same as it is in the water around it. The oxygen reduction reaction cannot continue in the crevice area, causing it to behave like an anode in a concentration cell. This imbalance can create a corrosive microenvironment in the crevice, promoting further metal dissolution and leading to acidic conditions with high chloride ion levels. The metal ions generated from this corrosion easily react with water, releasing protons, acid, and forming corrosion products. Concentration cell corrosion can be very aggressive and is caused by differences in the environment on a metal's surface. Even seemingly harmless atmospheres can lead to serious corrosion, as shown in an example of aircraft corrosion called pillowing. The most common type of this corrosion is oxygen differential cell corrosion. It happens because moisture in a crevice has less oxygen than moisture on the surface. The lower oxygen level in the crevice creates an anode, while the metal surface exposed to the air acts as a cathode. Another specific type of crevice corrosion, known as filiform corrosion, occurs when harmful chemicals build up under a protective film that has been damaged. Severe crevice corrosion can also happen under insulation. Number 4 is filiform corrosion. Filiform corrosion is a type of crevice corrosion that happens under a damaged protective film, often starting from tiny defects in coatings. Lacquers and quick-dry paints are particularly vulnerable, so they should be avoided unless proven safe by experience. If a coating is needed, it should allow little water vapor to pass and stick well. Zinc-rich coatings are a good choice for carbon steel because they offer cathodic protection. Number 5 is pack rust. Pack rust is a form of localized corrosion typical of steel components that develop a crevice into an open atmospheric environment. This expression is often used in relation to bridge inspection to describe built-up members of steel bridges that are showing signs of rust packing between steel plates. Images courtesy of Wayne A. Sinek, Termorust. Number 6 is galvanic corrosion. Galvanic corrosion occurs when two different metals are connected in a corrosive environment, such as water. In this situation, one metal acts as the anode and corrodes faster than it would alone, while the other acts as the cathode and corrodes more slowly. The level of corrosion can change depending on the presence of the other metal. When two metals touch, the anode's corrosion increases, and the cathode's corrosion decreases or stops. This principle is the basis for many corrosion monitoring techniques. The driving force behind galvanic corrosion is the difference in electrical potential between the metals. This concept was first explored by Luigi Galvani in the 18th century with experiments involving frogs. In 1800, Alessandro Volta created the first battery using different metal discs separated by a moist material, which laid the groundwork for modern batteries. In the 19th century, scientists like Sir Humphrey Davy and Michael Faraday applied this principle to protect metal structures using sacrificial metals like zinc, magnesium, or aluminum. In a bimetallic couple, the less noble metal becomes the anode and corrodes more quickly, while the more noble metal becomes the cathode. Galvanic corrosion is common and can be very damaging. The nobility of metals can be measured by their corrosion potential, and the galvanic series ranks materials based on their tendency to corrode in seawater. A small ratio of anode to cathode area can worsen corrosion, leading to rapid deterioration of the anode. To address galvanic corrosion, it's best to design systems to prevent these issues from occurring. Galvanic corrosion can happen on both large and small scales, including within the microstructure of materials. Number 7 is lamellar corrosion. Paul Dillon, an expert on materials and corrosion, explains that lamellar corrosion, also known as exfoliation, is defined as corrosion that spreads laterally along planes parallel to the surface, often at grain boundaries, and creates a layered appearance. This type of corrosion is not limited to aluminum, although it primarily affects aluminum alloys. Greg Coburn notes in his work that exfoliation begins at surface initiation sites and follows intergranular paths. Don Sprouse discusses testing methods for evaluating exfoliation. The NACE manual previously did not mention exfoliation, but later updates included case studies on aluminum exfoliation. While aluminum corrosion is more widely acknowledged, the term exfoliation also applies to cupronickel and ferrous alloys, where it involves excessive internal oxide growth that can damage equipment. Given its broader application, lamellar corrosion is a more inclusive term. Dillon suggests that the glossary should be updated to reflect this broader understanding. Now, let's move to Group 2, corrosion identifiable by supplementary means of examination. Number 1 is erosion. Erosion corrosion occurs when the movement of a corrosive fluid against a metal surface speeds up corrosion. For instance, pitting inside tubes can create turbulence, leading to faster corrosion and potential leaks. Poor workmanship, like leaving burrs on cut tube ends, can disrupt smooth water flow and increase erosion. This issue is significant in offshore well systems dealing with sand-laden liquids. Choosing the right materials is crucial to reduce erosion-corrosion damage. It's important to note that just because a material is hard doesn't mean it's resistant to erosion-corrosion. Good design is key, for example, lowering fluid velocity and promoting smooth, laminar, flow, using wider pipes, avoiding rough surfaces, and preventing turbulence and abrupt flow changes can help. Tank inlet pipes should be directed to the center of the tank, and pipe sections must be properly aligned. Impingement plates or baffles that can be replaced should be used to absorb impact. Additionally, increasing the thickness of vulnerable areas and using replaceable tapered ferrules in heat exchanger tubes can offer protection. Environmental measures like filtering abrasive particles from fluids, using water traps in steam and air systems, and employing deaeration or corrosion inhibitors can further reduce erosion-corrosion. Cathodic protection and protective coatings can also help slow down the deterioration of materials. Number 2 is cavitation erosion. Cavitation happens when a fluid's pressure drops too low and creates air pockets or bubbles that form and collapse. This can happen quickly and create steam, which is a problem if the fluid is supposed to be cool. Cavitation can cause damage to pumps, valves, and other equipment, and can lead to cooling problems. It's most likely to occur at the suction of a pump, near valves or pipe bends, or when there's a sudden pressure drop. To prevent cavitation, designers should reduce pressure gradients and avoid areas where pressure drops can occur. Additionally, using protective coatings or cathodic protection can help control cavitation. Number 3 is fretting corrosion. Fretting corrosion is a type of damage that happens when two surfaces move against each other, like in machinery or bearings, and are rubbed by vibrations. This movement scrapes off a protective coating on the metal and exposes it to the air, making it corrode. Fretting corrosion can occur during transportation if surfaces are exposed to vibrations. Number 4 is intergranular corrosion. Metals and alloys have a structure made up of grains, which are separated by grain boundaries. Intergranular corrosion occurs when there is localized damage at these boundaries, while the rest of the grains typically remain unaffected. This type of corrosion is often due to impurities accumulating at the grain boundaries or specific phases forming there, which can weaken resistance to corrosion nearby. This corrosion usually happens because certain elements segregate at the boundaries or form compounds that make the boundary areas more susceptible to attack. Consequently, the grain boundary zone becomes anodic compared to the rest of the surface, leading to corrosion that follows the grain boundaries. In severe cases, entire grains can break off due to the deterioration of their boundaries. Such corrosion can significantly impair the material's mechanical properties. A well-known case is the sensitization of stainless steels or weld decay, where chromium-rich precipitates at the grain boundaries deplete nearby chromium, making those areas more vulnerable to corrosion in specific environments. Reheating welded components during multipass welding often causes this issue. In austenitic stainless steels, interactions between titanium or niobium and carbon can lead to carbides forming in the heat-affected zone, causing a specific type of intergranular corrosion called knife line attack. This occurs near the weld bead due to rapid cooling preventing proper diffusion of materials. Reheating the welded area can help resolve the knife line attack problem. Number 5 is exfoliation. Exfoliation corrosion is a type of intergranular corrosion that occurs in high-strength aluminum alloys. These alloys, especially when extruded or heavily worked, have flattened, elongated grains that make them vulnerable to this type of damage. As corrosion builds up along the grain boundaries, it creates pressure that causes the grains to lift apart. This damage often starts at the ends of grains found in machined edges, holes, or grooves and can spread throughout the entire piece. The image of the exfoliation of an aircraft component illustrates how corrosion forms distinct layers that expand to cover a larger area than the original part, which has lost its structural integrity. Number 6 is dealloying, or also called selective leaching. Dealloying, or selective leaching, is the process of removing one element from an alloy through corrosion. A common example is the dezincification of brass, where zinc is lost, leaving a weak, porous copper structure. This can happen evenly or in specific areas. It's hard to explain dezincification just as zinc dissolving; instead, brass dissolves while zinc stays in solution and copper comes out of it. Another example is graphitic corrosion in gray cast iron, where the iron dissolves preferentially, leaving a brittle graphite structure behind. The term graphitization is often used for this but is not recommended since it can confuse discussions in metallurgy. During graphitic corrosion, the porous graphite, which makes up about 4 to 5% of the cast iron's mass, gets filled with insoluble corrosion products. This means the cast iron retains its appearance but becomes structurally weaker. To identify this corrosion, one can scrape the surface with a knife and see the iron crumble beneath. If the corrosion is extensive, the best option is usually to replace the damaged part. Let's now move to Group 3. Corrosion verification by microscopy. Number 1 is environmental cracking. Environmental cracking is a type of corrosion cracking that occurs under specific conditions, leading to forms of damage such as stress corrosion cracking or SCC, corrosion fatigue, and hydrogen embrittlement. This cracking is caused by various stresses from processes like cold work, welding, or grinding, and these stresses must be tensile to be effective. Cracks typically form at right angles to the tensile stresses at much lower stress levels than would normally cause a fracture without the corrosive environment. As cracks grow deeper, they weaken the material until it fails due to overload. SCC happens when metals are in an environment that would not damage them if there were no stress. For example, stainless steel pipes or valve stems in the nuclear industry can develop SCC. Stress cells can occur within a single piece of metal where some parts have more stored strain energy than others. Metal atoms are most stable in a regular crystal arrangement. When this arrangement is disrupted, several factors can lead to increased strain energy. The first is grain boundaries. Second is high localized stress. And the third is cold working. Grain boundaries. At the edges of metal crystals, atoms are less stable, leading to higher strain energy and increased corrosion at these boundaries. High localized stress. Areas under high stress have higher strain energy and can corrode faster than lower stress areas. For instance, loaded bolts usually corrode more than unloaded ones. It's best to use fasteners that are more cathodic compared to the metal they are securing to avoid corrosion. Cold working. Areas of metal that are cold worked have more dislocations, making them more anodic and prone to corrosion compared to non-cold worked areas. For example, a bent nail often corrodes at the bend or head where it was impacted by a hammer. Number 2 is stress corrosion cracking or SCC. Stress corrosion cracking happens when a material cracks due to a combination of tensile stress and a corrosive environment. SCC's effects typically lie between dry cracking and fatigue. Tensile stresses can come from direct application or residual stresses. This issue can be quite complex, especially in buried pipelines. Processes like cold deformation, welding, heat treatment, machining, and grinding can create residual stresses, which are often underestimated. Residual stresses from welding can be close to the material's yield strength. Additionally, corrosion product buildup in confined spaces can cause significant stresses. SCC usually occurs under certain combinations of alloy, environment, and stress. Usually, most of the surface stays untouched, but tiny cracks penetrate the material. These cracks can appear either between the grains, intergranular, or through the grains, transgranular, at a microscopic level. On a larger scale, stress corrosion cracking or SCC looks brittle, making it a severe type of corrosion. Detecting these fine cracks is hard, and predicting damage is challenging. Experimental data on SCC is very varied, and failures can occur suddenly with little loss of material. The first image shows intergranular SCC in an Inconel heat exchanger tube, with cracks along the grain boundaries. The second image shows SCC in a 316 stainless steel piping system, characterized by branched, lightning bolt, transgranular cracks. Images provided by Metallurgical Technologies Incorporated. This severe form of corrosion has led to notable failures, including the swimming pool roof collapse in Uster, Switzerland, and the Boeing 747 crash in Amsterdam. Chloride stress corrosion, significant for the nuclear industry, is a type of intergranular corrosion that occurs in austenitic stainless steel under stress when oxygen and chloride ions are present in high temperatures. It likely starts with chromium carbide deposits on grain boundaries, making the metal susceptible to corrosion. To manage this corrosion, it's crucial to keep chloride ion and oxygen levels low and to use low-carbon steels. Despite thorough testing of Inconel for certain uses, it still faces corrosion issues. Heat treating Inconel at 620 degrees Celsius to 705 degrees Celsius can improve its resilience against caustic stress corrosion cracking, depending on its prior treatment. Other issues with Inconel include material loss, tube denting, pitting, and intergranular attack. Corrosion fatigue is when a material gets damaged by repeated stress and exposure to a corrosive environment. This can lead to a rupture of its protective layer and accelerate corrosion. A material's resistance to repeated stress can be weakened by a corrosive environment, reducing the load it can handle and shortening its lifespan. Corrosion fatigue is different from normal fatigue because there is no minimum stress level a material can handle without breaking. Corrosion fatigue is often found in combination with fretting, a process where metal is worn away by friction. In a corrosive environment, a material's resistance to repeated stress can be significantly reduced, sometimes by up to 75%. No metal is completely immune to corrosion fatigue, which can occur even in mild corrosive environments. Controlling corrosion fatigue involves reducing the stress a material experiences or taking measures to prevent corrosion. Number 4 is hydrogen embrittlement. Hydrogen embrittlement is a type of damage caused by hydrogen entering metals, mainly linked to corrosion. This can weaken a material, making it less flexible and causing cracks or failures even under low stress. It commonly affects high-strength steels, titanium, and aluminum alloys. The problem is not fully understood, and detecting it is particularly challenging. Sources of hydrogen. Hydrogen can enter metals during various processes, including steel production, welding, and when hydrogen is used in environments like nuclear reactors. It can also come from corrosion, like rusting. Here are some ways hydrogen can enter metals. The first is manufacturing. Operations like welding and electroplating can cause hydrogen absorption. To remove it, parts may undergo heat treatment. The second is corrosion byproducts. During corrosion, some hydrogen may enter the metal instead of escaping as gas, leading to problems similar to stress corrosion cracking. If hydrogen sulfide is involved, it may cause sulfate stress cracking. The third is cathodic protection. If not controlled, this method used to prevent corrosion can also lead to hydrogen entry. Hydrogen embrittlement in stainless steel. When hydrogen enters stainless steel, it can form methane gas along grain boundaries, creating pressure that leads to cracks. Hydrogen embrittlement is a major reason for maintaining certain pH levels in reactor coolant to avoid issues, especially in systems without aluminum. Under high stress, failures can happen. At room temperature, hydrogen gets absorbed into the metal and moves through it, often gathering at defects. If stress causes cracking, it typically follows the metal grains. At high temperatures, hydrogen accumulates at the grain boundaries, leading to different types of cracking. Importantly, hydrogen embrittlement isn't permanent. If the metal is in a different environment and no new hydrogen is produced, the hydrogen can disperse, restoring the metal's flexibility. To combat hydrogen embrittlement, efforts focus on reducing residual hydrogen in steel, minimizing hydrogen pickup during processing, creating more resistant alloys, and developing coatings that reduce embrittlement. Thank you.